Hi, I'm Kat. I'm doing a workshop for Aztec. We're going to cover Noir. Aztec is a layer 2, privacy first, layer 2 on Ethereum. And we have like 5K of bounties that we're giving out for this hackathon, a bunch of different things that you can build on Noir and on Aztec. We do have a programming language called Noir. It's how you write circuits, like ZK circuits. If you've never heard of them, that's cool. You don't have to. I'm going to like cover that today. So yeah, today, kind of going to introduce Noir, like setting up a project, going through it, verifying proofs and making proofs and stuff like that. We're also going to just talk like a bit about just an introduction into circuits and how to get an intuition of how ZK works. Then I want to explore the Alibaba cave, which is a really common like thought experiment for understanding ZK, and go a bit more into it in a more like up-to-date version of what ZK looks like these days. And then we're going to use those new Alibaba cave intuitions to look at circuits in Noir and see what they look like and how you can use them in your own stuff. So, yeah, Noir is like, it looks like this. If you've ever used Rust, it looks exactly like Rust. The syntax is pretty much copied and pasted from Rust. There's a few different things that you have to kind of be aware of so you get that intuition for ZK, but it looks exactly like Rust. The whole point of it is that you're like writing code, not circuits. You don't have to really think too hard about ZK and stuff like you would with Circum. It's also proving system agnostic. If you're familiar with ZK, you'll maybe understand what this means, but it compiles down into like this like intermediate kind of representation of what circuits are, and you can use it with our proving backend called Brettenberg. You can also use like Graph16 or any proving system that you want, which is pretty fun. So you can like explore what's different, what's compatible with different proving systems and write Noir to do it. This is what something looks like. I'm gonna actually like code this in a second, but yeah, you'd call your main function main. It has to be called that, and it's gonna take in x, which is like a private parameter. It's just like private by default, and then a public parameter, which is also a field of y, and it will say assert that x and y are not equal. If that's cool, then the code will work and the proof will be generated. So it looks really simple. That's literally an entire Noir project. So yeah, if you want to like follow along, I've got this GitHub repo that I'm gonna go through. It's just like a few different example circuits you might want to look at, and also some stuff with Solidity as well. So recommend like just scanning that. I'm gonna leave it up for a bit so you can have a look, and we'll go through it as well together. Okay, I see no more phones, so I think we're good. All right. Before I dive into that, if you are unfamiliar with Alibaba Cave, I tried to make one, and it doesn't look very nice. I did it in Canva. But this guy, this is Victor. He's our verifier. This woman is Peggy, who's our prover. There's two different like entities with ZK, and those are what you need to be aware of: verifier, prover. They do different things. They have different information. So we've got our Victor. We've got this cave, and there's a gate for this cave. There's like a code to open this gate. Peggy knows what the code is. Victor doesn't. Victor wants to prove that Peggy knows what the code is. So Victor's like, okay, you're somewhere in the cave. I don't know where you are. You need to come out of the B pathway. And she's like, okay, I'm going to open the door and I'm going to come out B. And Victor's like, okay, cool. So you might have known something. You came out of B. So you might have known it, or you might have just started in B. I don't know that. So this repeats like 50 times. And basically by the end of it, we've proven that Peggy knows the code for this gate, but never had to tell Victor what the code was. She's just proved that she has that knowledge. That's what ZK is. So yeah, I'm actually just going to go into the repo now. And can they hear me if I'm just talking? Because can you hear me like back there? Okay, I'm just trying to code, so it's like going to be hard. Okay, cool. All right, so this is supposed to clear.
Hold it.
Can you hold it for me?
Yeah.
Okay, thanks. Oh, yeah. Thanks, Ola. This is Ola. If you need some help with Aztec stuff, he can also help you. He knows, he likes Noir. Okay, so In this GitHub repo, I've got a few different examples of stuff. We've got simple, which is just that thing that you saw over there, like x is not equal to y. We've got intermediate, optimizing, and recursion. I'm going to go into those soon. But right now, I'm just kind of going to explain to you like how you would start a Noir project. So in my terminal, if you go to like the Noir docs, you'll be able to see how to install it in the Getting Started guide here. Install Nargo, and you just copy this and do Noir up. So it's noir-line.org. Pretty simple to do. So do that before you do any of this. And when we've done that, I'm going to create a project in Simple. So I'm just going to delete my circuits. Am I actually? Yeah. So I'm going to create a new project by just going Nargo new. I'm calling it circuit. And then it's created this new project, this Noir project. So if I just cd into circuit here, I can see we have a Nargo toml and a source directory. So I'm going to open this whole thing in VS Code. I'm assuming you can see that. So it's a circuit. Nargo toml looks a bit like this. It's basically just saying that it is a circuit, and we're using this compiler, this version of Noir. This is the most latest version, so I recommend using that one. And also inside the source directory, we've got main nr, and this is what I was kind of talking about earlier. So we've got a main function, and we've got a test as well, which you dictate with something like that. I'm not going to go through that today. That's a bit like out of scope for this workshop, but this is what it's doing. So in order to like play with this, I'm going to open my terminal. So when we're in the directory that has the Nargo toml, we can create this thing called a prover toml if we do Nargo check. And this creates this, which is kind of like our concurrent system. So these are our inputs for our function. So we have x and we have y. X is going to be private, y is public. So if I put in like 1 and 2, then theoretically this should pass because it's saying that 1 is not equal to 2. And then we can do Nargo execute. And this will generate the witness that we need to use in order to create the proof. So if we go into target, we can see like our compiled JSON of this circuit here. This is going to be really useful. It's just like kind of like an ABI if you're using that. This is our witness. It looks a little bit like this. Doesn't have to make sense right now. We can use that with a Nargo pretty simply. So then we're going to use our Berettenberg backend. Noir out of the box comes with something called Berettenberg. It uses like a kind of Plonk proving system, and it's written in. You can have a look at it if you want, but it basically lets you like generate proofs and verifiers and stuff. So we're going to use Berettenberg with BB prove. Thank you for holding this mic. Sorry. Thank you for holding the mic. We're going to pass in the path to the circuit that we compiled here. So it's inside target, what's it called? Circuit, what the heck? Circuit.json. And then we also need to pass in where we want the output to be. So we'll do target. We'll just call it proof. And then we also need to pass in the witness that we already generated here. So we'll do target / witness. So we're not going to see anything pop up here, but we should see a proof here inside our target because we specified that's where we want it to go. And it looks like that. You can also get this in like a hexadecimal format if you're using JavaScript. But if you're just going to be working with Nargo, like that's what it looks like. You don't have to care.
It's binary.
Thanks, Ola. And then in order to verify that, we can create a verification key also with Berettenberg. I need to see my computer. So we'll do VB write VK. We'll pass in the compiled circuit again and the output, which will be target / VK. We got it here, another binary file. And then we can also verify from Berettenberg. So we'll just do VB verify. We'll pass in the verification key and the proof that we have here. So if nothing comes up, that means it's like a correct verification. It'll give you a failure if it does verify. So we could just do like pass nothing, and then it'll give you some sort of error. So that's kind of how Noir works, simply, like from the beginning. We can also generate a contract with it. So you can verify like directly from your machine using Nargo, and you can also create a verifier in Solidity. So you can verify stuff on chain. So you'll still be creating the proof locally on your machine, and then you can pass it into like a smart contract with the public inputs and verify it on chain. And that's like a kind of common thing that people do. So if we want to do that, we can just, like where our Nargo toml is, just do bb contract, and we'll see a contract.solidity file here. And it's pretty crazy. There's a lot of like assembly and stuff in here. I have no idea what this stuff is, and I've never really read it, but there you go. So we'll just go through like kind of an example, I guess, of Solidity. So I've got this contract here, which just calls our verify function that we have in here. Where'd I go? And yeah, if there's a proof result, then it'll prove it and say it logged with root, and then it'll say proof is not valid if it doesn't work. And I also have this test. So in this test, we're using Noir.js. You can actually like generate proofs directly within the browser with this as well. And you can, so what I'm doing with this is like setting up Noir and then creating the proof and calling our contracts with this proof to make sure everything's cool. So I think I need a node. Hold on. I'm just going to run hard hat node. That's and then I'll just run this test here. Okay, it didn't work. What does not exist? Oh, I've called it something. Okay. Hold on. What? Circuit target.
Circuit, twice. Remove the circuit before target. Yeah, remove.
I don't think it's right. It's not gonna work either. Oh, okay, cool. Thanks. So yeah, so what we've done here with Noir.js is we've like created a proof with generate proof, and we've passed this to our Solidity verifier, and then we've verified it on chain that everything is cool. I guess we can go through a failing one as well. So if we wanted to fail, yeah.
So the verifier is generated
The what?
The verifier is generated Solidity, right?
Yeah.
And so what inputs do you pass to that verifier? Is that one for that specific witness and proof, or is that just for?
It's specific for this circuit, yeah. So you pass in the proof and public functions to the verify function, the public inputs. Yeah? Okay, cool. So, anyone else have any questions about just like Noir fundamental stuff? No? Cool. So I guess we can move on to like more Alibaba Cave ZK intuition. Yeah. Thanks, Ola. So, yeah. So in our like previous Alibaba Cave example, we saw that Victor had to keep asking this to Peggy, like, you know, hundreds and hundreds of times to ensure this is actually correct. But we don't have that anymore with something called snarks. That's like the general ZK that we use. Snarks means that it's non-interactive. So the verifier you can't keep asking questions to Peggy. So in order for this to work, it introduces like a trusted setup. Usually there are like snarks that don't need it, but for the case of Aztec and Noir, we do use a trusted setup. This third party creates like randomness, so Peggy can like randomly do stuff, and then Victor uses this third party as well to like kind of help to verify the proof that Peggy passes to it. So you can have your trusted setup like decentralized. Obviously, I've got some questions about that recently, but yeah, so the trusted setup, it is something that you trust, but it can also be like in a decentralized way. So to kind of see what that looks like, we've got our little light bulb as like the trusted setup, and it's doing the random thing, like come out of B, come out of A, randomly saying like, this is the kind of thing that you want to do. So Peggy is doing all the things that the trusted setup tells it to do, going out of B and A, and then like taking photos of each path to prove that she was there, which then like proves obviously that she does know the key. Eventually, when she passes all these photos to Victor, Victor checks with the trusted setup to get this key that he needs, and then it's like, okay, cool, your proof is all good. Here. So that's kind of like the way that it works. Now, what that means as well is that we can't have like stuff in circuits like randomness or external parameters, and you kind of need to know the size of the circuit like when you're compiling it. So there's a lot of things like maybe within Rust that you'd be used to, or other programming languages, where like you can kind of introduce some parameter later that might be dependent on something or something external, or you can have randomness and the size of the program, you don't know it, like it could change. So I've got some examples here in like the intermediate thing for different loops that you can do in Noir. This is actually really cool because like in a lot of ZK things you just can't accomplish this kind of thing. But you won't be able to pass in like an arbitrary array that you don't know the size of. You will always have to know the size of the loop or the array that you need to go over. So these are like different kinds of loops that you can do in Noir. So yeah, for like 4 sub-integer in something like this, so like 0 to 5, so it would just go 0, 1, 2, 3, 4, 5, and then it prints I. You can also have like an array of fields here, but you have to specify the size of the array, so obviously it's going to be 3. And then you can go through it like this. You can get the length of it. And yeah, for element in foo, so we have foo specified here. Different types of 4s. I've got this as well because like it is possible to do breaks and continues, which maybe doesn't particularly make sense because we said that the size of the circuit, you have to know it on compile time. But you can use something called unconstrained functions. I'm going to get into this a little bit later as well. But unconstrained basically means they're not actually part of a circuit. They're unconstrained, so there's no like proving happening here, but you can do things like break and continue and have like arbitrary size stuff within an unconstrained function, which could be useful for optimizing certain things. So if we go back to our slideshow, yeah, something that's really important with writing circuits is that right now we're still working on a lot of optimization for proving backends, and I know Aztec has done a bunch of stuff for that kind of thing, but it's still relatively slow, and you can't just like kind of where we are with programming now, you don't really have to think too much about optimizing anymore, but with circuits you still do. So you really want it to be as little as possible, especially because people are running these circuits locally in order to generate their proof. So you really need it to be fast. It'll take minutes sometimes to do it within a browser, and if it takes longer than that, then you're messing something up. So you really have to think about having fewer and fewer gates that Peggy's going through. And try to make them smaller. Wait. Yeah. Okay, this is an image that I made. So there's lots of different gates that Peggy's having to go through and take photos of and open different gates and do different things, and that's obviously going to be more expensive. And there are a lot of ways to optimize within Noir. We have a lot of libraries that are specifically optimizing different signatures, verifications and things like that, and we're still working on that. So that's there's an open bounty for building signature libraries and making them faster if you're up for that. But something that is pretty cool that you can use for it is unconstrained functions. So this is an example. This num should probably be a field, not U32, of a square root function. So you could do this all inside the circuit, and that's going to take forever. You could go through each number and calculate the square root of it and divide it and do all this general square root function inside a constrained function. Or what you could do is do it inside an unconstrained function, you square root it, there's not going to be any like circuit that's generated for this, it's just like regular kind of code. And then you can prove that that is actually correct inside a constrained function by squaring those numbers together. So it's quite like an interesting way to think of like how can you prove that something has been executed correctly in an unconstrained function within a constrained function, but it's a cool thing to look at. And this is just an example of that, using unconstrained functions in a fun way. And I don't think I need to do that one. Yeah, so you can't like access, it's the same kind of thing I was talking about, it's sealed, so you can't access like public information that's out there in the world, because everything is done like on your machine when you're generating a proof. So if you're gonna do that, you have to use like oracles, and then that's another trusted data source. So there's ways that you can do that to help. But this is another cool thing that Noir can do, and it's recursion of proofs. So it's kind of like, you have all these like inner proofs. I'll get that later. That you can do a proof, and then you can like have this proof and pass this proof over to another proof who can then verify that proof is right, and pass that proof to another proof, verify these proofs are right, and keep on doing that. So it means that the final proof, you only have to verify one time, and you've actually verified like a bunch of proofs. So that's kind of how ZK rollups actually work, and you can do it within Noir, and there's a bunch of like things you can kind of do with it. So an example could be a game or something, like you have a 2-player turn-based game, and you do something and you prove that was right, and then you pass your proof to the other person, and they do their turn and they prove that was right, and they pass it to you, and then you verify that theirs is true and yours is true, and you keep on going, so that at the very end, when you do have that like solidity verifier on chain, they're only verifying one proof, and it's a lot faster. So it's pretty cool. This is what it could look like. So we've got Peggy like on the inside of this proof, and she's taking photos and then giving it to Victor, and Victor's like, cool. And then Victor moves on to this like next proof, and she goes around and verifies her own proof and passes it to Victor by the end, and then they're only verifying one proof. Is there a fly? So this is what that looks like in Noir. So you need like multiple circuits, because you have one circuit that's going to verify the other circuit, and then you have your circuit that's like the inner circuit. So this is just the one that we're used to. We specify it as recursive, and that's it'll compile in a slightly different way if you're saying like this is going to be inside a recursive proof. So make sure this is recursive. And then within our recursive proof, we're taking in that proof, and then we're calling like verify proof and verifying it, and then you'd also want to do something here, but I haven't put that. So this is how you verify the proof within another proof. I think. Yeah, this is all I wanted to cover today. So I've gone pretty fast. But this, if you're like trying to hack on Aztec and Noir for this hackathon and you want to keep playing with it, or you don't have time to look at Aztec, we are running this thing right now called Alpha Build 2. It's our second iteration of this thing called Alpha Build, where we're just looking for people to come in and build cool stuff with Aztec. It's like a virtual hackathon. It's going on for about a month. We have 100K of prizes in total, so that's going to be pretty cool. So I recommend signing up for that, and we'll just give you some information about what that is. The specific thing that we're kind of looking for this is like identity, account abstraction, so one of the tracks of this hackathon. But yeah, that's the end. Thanks, guys. Do we have any questions right now? No?
What would you like to see built?
Yeah, so we do have like this hacker. Let me see if I can find it. If you go into the hacker manual that ETHRome sent out, we have some ideas in here. There's loads. We don't really have like a limit of what we want to see built, because there's so much you can do with ZK. But we're kind of looking, I think our main focus right now would be on things like identity and gaming. So There's like sign-in solutions you can use. We have people who are currently building ZK Passport and ZK Email on Noir, and to plug into those and like build applications with that would be really cool. So like ZK Email, you can basically prove anything from any email without revealing the email address that it was sent to. So you can say like, yeah, I do have a Twitter following of like a certain amount because you prove that you own a Twitter profile with that amount because you have an email from Twitter that says that, but you don't have to reveal that like Twitter information. And there's also ZK Passport, which is, I think, pretty self-explanatory. You can like prove anything from your passport, such as you are an Italian citizen, without giving away how old you are or what your name is. Fun fact, they're actually partnered with DevCon, so people from Southeast Asia can like prove that they are from Southeast Asia and get a discounted ticket without giving away all their information. So yeah, I think stuff like identity, login solutions are really, really cool with Noir, or like, yeah, gaming as well. So kind of like turn-based games is cool. Also, if you know anything about cryptography and like Circum libraries, trying to convert them into Noir would be cool. We're working with ZK-Kit with PSE. Adding to that is awesome. But I think for the purpose of the hackathon, applications are cool. So yeah, on the hacker manual for ETHRome, where are we? If you go to prizes and bounties and then click on Aztec, we have some like themes and stuff here. And then you can head to our website as well, and there's like a bunch of other ones, applications and libraries, all within Noir. So yeah, good question. Thanks. Any other questions? Yeah. The what?
I didn't quite get the constrained and unconstrained.
Yeah. So constrained and unconstrained functions. Constrained functions will be actually within the circuit and proved. So I just opened my Slack, sorry about that. So like anything that's inside a function that's just called function. Let's open it. This will actually, like your proof will go through this is proved. Anything in here is not actually proved, it can just return values. So you can do any sort of like arbitrary calculations in here within Noir. But it's just like console logging anything you want, and then you can pass it back to like a constraint function to prove it. But yeah, this is a constraint, this is speedy, and there's no circuit. It's not like in the circuit itself. Yeah, it's like, what? Untrusted. I don't want to use that word because I don't want to say this is trusted. It's more like you cannot rely on the information from this one, but this one is like, it's an actual proof that you can verify. Yeah. Cool. All right, thanks everybody. Here's AV2 again if you want to scan this.